Here, since we have previously downloaded, so I will repeat the installation here. Here, according to our hands of the development board to choose the chip model, such as my hands is STM32 F411C6. There are 4 options here: kernel, device driver. This configuration needs to be ported manually. Shell Finch component, libpool, CPU architecture assembly. Here we check kernel, shell, and libpool, with kernel and libpool being mandatory. Our TOS thread needs to be checked here. Here you can see the configuration type and related configuration description. Expand below to see the specific instructions for each configuration item, which you should remember to read. To make it easier to observe the phenomenon, we turn on Finch component support and leave the rest as default, while Finch relies on semaphores, which are enabled in the default configuration. Enable USAT1 as a Finch serial device. Debug select serial wire. Next, configure the interrupt information. Hard fault is taken over by the TOS by default. Here we turn off the enable. Next, configure the project name and tool time. Select the NDK. After entering the MDK, compared to the base project, we can find a few new groups added. Shell, RT thread Finch component. Libpool, architecture port files for RT thread. Kernel, RT threads kernel file. In the board.h file, you can modify the dynamic memory heap according to your needs. Of course, you have to turn on the heap supporting CubeMX. We will have to talk about it later. If you are using the Finch component, modify the serial port entries here according to the previous CubeMX. Next, we add a delay to the main function to make it easier for the Finch thread to get scheduled. Next, we compile and download the project. We open the serial port tool and observe the console phenomenon. You can see that Finch started successfully, and also supports a variety of preset commands. This example creates two threads, one dynamic and one static. Since we are using dynamic thread creation, we need to enable dynamic heap management, as well as enable the minimum memory algorithm. This routine creates a thread that enters the idle task hook by delaying it, which is used to print the number of times the idle hook was entered. Enable using hook. Again, since the example uses dynamically created threads, dynamic heap management needs to be enabled, as well as the minimum memory algorithm. Add examples and compile and download to see the phenomenon. This example demonstrates printing thread switching information in a scheduler hook. The dynamic heap management and minimum memory algorithms are also enabled here. Enabling using hooks and forward capaciable hooks. Next, add the example and compile the download to see the phenomenon. The program will initialize two threads and initialize a static event object, where one thread waits on the event object to receive the event, and the other thread sends the event, event 3, event 5. Enable event set control macros. Add examples and compile and download to see the phenomenon. The program creates two static threads, a static mailbox object, one of which sends mail to the mailbox and one of which receives mail from the mailbox. Enable mailbox control macros. Add examples and compile and download to see the phenomenon. The example creates two dynamic threads, one that receives messages from the message queue and one that sends regular and urgent messages to the message queue at regular intervals. Enable message queue control macros. Add examples and compile and download to see the phenomenon. This example uses Mutexes to implement protection of critical values into threads. Enabling Mutex control macros. Since we use dynamically created Mutex locks, we need to enable dynamic heap management, as well as the minimum memory algorithm. Add examples and compile and download to see the phenomenon. The example creates a dynamic semaphore, initializes two threads. Thread 1 sends a semaphore every 10 counts of count, and thread 2 receives the semaphore and adds 1 to the number. Semaphores control macros are enabled by default. Again, since we are using dynamically created semaphores, we need to enable dynamic heap management, as well as the minimum memory algorithm. Add examples and compile and download to see the phenomenon. The example creates a thread. The thread installs the signal, and then sends the signal to this thread. Open signal control macros. Because we use dynamic thread creation, we need to enable dynamic heap management and the minimum memory algorithm, and because signal initialization relies on the memory pool mechanism, we also need to enable mempool here. Add examples and compile and download to see the phenomenon. The example creates a dynamic thread that dynamically requests memory and frees it, requesting a larger amount of memory each time, and terminating when it can't be requested. Here you can modify the size of the dynamic memory heap according to the onboard RAM. Enable dynamic heap management and minimum memory algorithms. Add examples and compile and download to see the phenomenon. The example will create a static memory pool object with two dynamic threads. One thread will try to get a block of memory from the memory pool, and the other thread will free the block. Enabling memory heap, memory pool, and minimum memory algorithms. Add examples and compile and download to see the phenomenon. The routine creates two dynamic timers, one single and one periodic, and the periodic timer runs for a period of time and then stops running. Enabling memory heap and minimum memory algorithms. Add examples and compile and download to see the phenomenon. This example demonstrates global variable access with interrupts turned off. Enabling memory heap and minimum memory algorithms. Add examples and compile and download to see the phenomenon. This example will create 3 dynamic threads to check that when holding a mutex, the priority of the holding thread is adjusted to the highest of the waiting thread priorities. Enable mutex. Enabling memory heap and minimum memory algorithms. Add examples and compile and download to see the phenomenon. This program implements the producer-consumer model. Enable Semaphore. Enabling memory heap and minimum memory algorithms. Add examples and compile and download to see the phenomenon.